Okay, so today we come to part 4 of chapter 5. Okay, so where we will talk about some special types of matrices that they have very nice properties on their eigenvalues and eigenvectors. Okay, so first of all, I want to give you a quick review on a concept which is known as the transpose of a matrix. So okay, so I believe that you know it already, but let me just quickly go through what does it mean by a transpose of a matrix. Okay, so suppose I have a matrix. Well, it can be an n by n matrix, right? But just make it simple. If I have this 3 by 2 matrix, so that is I have 2 columns, and then each columns I have 3 elements, right? So this is a 3 by 2 matrix. Okay, so I can just call this A. And then the definition of the transpose of this matrix A is that you are going to take the column as the row of the matrix. So that is, this is the first column, right? So, and then I basically make it to a row that has 3 elements. Okay. And then, so the first column becomes a first row. And then the second column becomes the second row. Okay. So now I form a new matrix. Okay, so originally I have this matrix A, which is a 3 by 2 matrix. After taking the so-called transpose, I have this 2 by 3 matrix, right? So columns becomes row. So that's that simple. Okay, so then for transpose, we use this notation, AT. So this 3 by 2 is this A, and then this 2 by 3 is this AT. So just a couple more examples over here, right? So whenever you have a matrix, okay, I don't care what dimension you have. Here you can as simple as just a 1 by 2 matrix, and then this taking this transpose becomes this one. And if you take this transpose back, it becomes this one. So over here, I have this matrix 1, 2, 3, 4, and then taking the transpose, as I said, right? So this this column over here, 1, 3, becomes the first row over here, 1, 3, and the second column over here, 2, 4, become the second row over here, 2, 4. Okay, so that's why the transpose of this matrix here is this one. And this one is similar to what I just showed you, right? 3 by 2, right? So each column, 3 elements, right? And then this first column becomes the first row over here. And then the second column becomes the second row over here, taking transpose. Okay. So that is, right? So in general, if you have an n by n matrix, right? So at the end, you will have an n by m matrix. And then the way to do the change is just you interchange the rows and columns, right? So that's it. Okay. And then the basic properties that's over here, okay, it's not going to prove them, but what you can see from here is that if you take the transpose and then take the transpose again, it becomes itself, right? So just like take this matrix example, if you take the transpose, it becomes this one. Take the transpose again, go back to this one. Okay. And then if you sum the 2 matrices and take the transpose, it will be equals to taking the transpose for the 2 matrices individually and sum them up. Okay. And also, if you want to take the inverse of the transpose matrix, it will be the same as taking the inverse first and then take the transpose. Okay. And then one more, this one which we'll actually use is that if you take the product of a matrix and then take the transpose, it will be equals to, okay, the second matrix transpose times the first matrix transpose. Okay. So these are the basic properties of the transpose of a matrix. Okay, so we'll talk about transpose of a matrix a lot. Okay. So I think this slide I showed you last time. Okay, in fact, we are going to talk about some special types of matrices. Okay, so first, don't care about the so-called complex matrices. So let's just focus on the so-called real matrices, where all the elements in the matrix are real number. Okay. So symmetric matrix is that taking the transpose of this matrix becomes the matrix itself, right? So I can give you a simple example. If I have this 1, 2, 3, 3. If you take the transpose, so what you have, right, is that, right? So this column becomes the first row, right? So this column becomes the second row. So you can see that here, taking the transpose with the same as before taking the transpose. Okay, so this is an example of symmetric matrix. And notice that symmetric matrix only possible if you have a square matrix, right? Because otherwise, if you have a 3 by 2, it becomes 2 by 3, right? So that's not possible that they become equal to each other. So it must be an n by n square matrix. So that's the first one we'll talk about. Okay, and then the second one is that the transpose of this matrix does not equals to the matrix itself, but instead is equals to the inverse of the matrix. Okay, so I will talk about that. Okay. So before talking about matrix, okay, so I also need to remind you one thing about the vectors. Okay, so in the last part of the chapters, we have talked about linear independence, right? So or linear dependence is that if I have take the most simple example, right? So if I have two vectors, right? So if they are not parallel to each other, then they are linearly independent, right? So that's what we learned previously. Okay. So this time, we want to also talk about the so-called the orthogonal, okay, or that means it's or perpendicular. So what it means is that again, if I just take two vectors, okay, so if they are perpendicular to each other, okay, so then I will say that these are two orthogonal vectors, or I would say that they are perpendicular to each other. And mathematically, how do you check whether the two vectors are orthogonal or not, right? So you do dot product, right? So because if you do dot product, so what you are actually taking is that if you have this matrix A over here, and then another, a vector A over here, and then another vector B over here, and you remember that the dot product will give you the product of the magnitude of the two vectors times the cosine of the angle between the two vectors, right? So that if you have this, assuming both are not zero vectors, right? So if you have theta to be zero, if you have theta to be 90 degrees, then this cosine theta will be zero. Then this A dot B will be 0, right? So if theta is 90 degrees. So then I think this is something you have learned already at some point, is that just taking dot product will actually help you to test whether the two vectors are perpendicular to each other or orthogonal to each other. And then here, okay, I want to first again go back to the column vector notation that we have, right? So if I have these two, suppose I have these two vectors, that so A is given by this A1 x hat plus A2 y hat, and if the B is given by this B1 x hat plus B2 y hat, right? So in the column vector notation, right? So I'll write this A as A1 A2, right? And then I'll write this B as B1 B2. Okay. And remember, if I use this x hat and y hat basis, when you take the dot product, it's very simple, right? So this A dot B is just given by A1 B1 plus A2 B2, right? And if I'm going to use this column vector notation for the vectors. So you realize that taking the dot products is basically doing the following. Okay, it's that I'm going to, so again, I have this A to be this one, B to be this one, is that you are going to take the transpose of one of the vectors. So let's say I take the A transpose. So what is A transpose? So A is a 2x1, is a column vector, or is a 2x1 matrix. So it's a 2x1, A1, A2. And then if I take the transpose of A, I will get this 1x2 matrix, or I call this a row vector. And then if I take this and do the product with the B vector itself, okay, so then this is what I call A transpose B, right? So it's given over here. Okay, so if we just do this matrix product, right? So you know how to do it. Just follow the matrix multiplication rule that you learned, right? So you realize that this one is exactly A1 B1 plus A2 B2. Okay. So that is in this column vector notation. If you want to take the dot product, just do this. Take the transpose of one of them, and then do the matrix product with the other. Okay. And of course, you will also realize that this is also the same as B transpose A. Okay. The two will give you the same dot product. Okay, so this is the notation that we'll use. Okay. Now, orthogonal I talk about, right? So and then take one step further. Is that the so-called orthonormal? So what it means is that, again, if I have two vectors, given that they are orthogonal already, okay, and also if the length of each vector is 1, okay, so that means both A and both B are unit vectors, then I would say that these two are orthogonal orthonormal vectors, right? So normal comes from, normalization, right? So normalize, so that means that you make that length equals to 1, right? So that's how this normal comes into this word, right? So orthonormal. Okay. So now I talk about two vectors, right? So now if I have a set of vectors, right? So let's say we won't really go that far, but let's say if I have n-dimensional space, right? So and then I give you n vectors, okay, and then if all these n vectors are unit vectors, and also they are all perpendicular to each other, orthogonal to each other, right? So in principle, you need to really consider all the dot products between the n vectors to make sure that it satisfies, right? So, and then that's the so-called orthonormal set of vectors. Okay. And then the orthonormal basis simply means that this orthonormal set of vector forms a basis of my vector space. Right? So then, of course, the most common example that you have been using a lot is, again, I consider a three-dimensional space, right? So if I consider a three-dimensional space over here, and then so 3 unit vectors that we always use is what is that? Is this x hat, y hat, and z hat, right? So clearly, so these three are these three vectors form an orthonormal set, right? So orthonormal basis for this three-dimensional space. And of course, it won't be the only choice. You could imagine that if you are going to rotate x hat by some degree and then rotate y hat by some degree, the same degree, right? So by theta and then by theta. So here I got this, I cannot call this x hat anymore. let me call this x hat prime and y hat prime, right? And then let's say the z doesn't change. So then, of course, your x hat prime, y hat prime, and z hat prime is also an orthonormal basis. Right? So now, what is not the orthonormal basis? Right? So you could imagine that if I have this x, y, z, but if this z is not pointing exactly up, right? So, but it's like tilted to one side, then that means this z won't be, this tilted z hat, right? So won't be perpendicular to, so if I put the z tilted this to one side, right? So then this z hat, of course, no longer perpendicular to the other two, then it won't be an orthonormal basis. Okay, I think this is all intuitive and not difficult to understand. And now, one thing is that suppose I just give you three vectors, okay, let's say in three-dimensional space, and then I ask you whether they form an orthonormal set or not. Okay, so then what you need to do, right? So as I said, you need to check whether each of the vectors has the length 1, right? And then you need to take the dot product of all the vectors to see whether they give you 0 if you take the two different vectors. Okay. So just to make it more tidy, let me just define a matrix. So I'm still considering three-dimensional space, so and then I give you three vectors, right? So and I ask you whether they form a orthonormal set or not, right? So let's say I give you this v1, v2, and v3 three vectors. Okay, I want you to test whether they're orthonormal set or not. So what I'm going to do is that I define a matrix P, which is formed by putting the three vectors that I gave you into three columns. Okay. And then you also consider the transpose of P. Okay. So then what is the transpose of P? The transpose of P would be, right, as I said, taking the column becomes a row, right? So this one is my V1 over here, right? And then here, okay, you understand the transpose. Okay, and then here, right, so V2, and then here, V3. Okay. Right, so column becomes row. So now, if you try to take the product between P and PT, right? So P or PTP. So what you have, right? So it's a matrix over here. So you can see that each element really is a dot product, right? So this element over here is a dot product given by V1 and V1 itself, right? So give you the first element. So then this second element over here is a dot product between V2 and V1. And then the third one, of course, is this V3 with V1. And then, well, similarly, you can write down all the others, right? So I guess I just write down a couple more. Right. So you can see that each element in this matrix, okay, is given by a dot product. Okay. And then the diagonal element really is the dot product of one of the vector with itself. Right. So V1 dot V1, right? V2 dot V2, V3 dot V3. Okay. If it is indeed a orthonormal set, then the dot product of each vectors with itself has to be 1, right? So because the length, I told you that the length has to be 1, right? And on the other hand, if you consider all the off diagonal elements, right? So all the off diagonal elements refer to a dot product between two different vectors. Right? And if they are orthonormal set, so then taking the dot product between the two vectors will be 0, right? So that means if they are indeed orthonormal set, then this matrix at the end will give you this, just an identity matrix. Okay. Right, so that is right. So to summarize, so if I give you a set of vectors, you want to test whether they form an orthonormal set. Just construct this matrix P using all the vectors, and then do this PTP to see whether it's an identity matrix or not. Okay, so then next, let's actually move on to talk about the properties of the symmetric matrix, right? So I already introduced it, right? So if that the after taking the transpose, right? So it's becomes itself, right? So and if you look at it, right, visually, really, it's like if you take a mirror to take this as a symmetric axis, right? You can see that this side, right? So look exactly the same as this side, right? This side looks like a mirror reflection of the other side. Visually, this is how it looks. So it can be shown that, and also not going to talk about the proof, but if I have this symmetric matrix, if you just take the product of this matrix and again, right? So a to the n, and that will still be a symmetric matrix. And if a symmetric matrix is invertible, okay, its inverse also will be symmetric. And also, if you find that there is another symmetric matrix B, and then if you do the product AB, where A itself is also a symmetric matrix, right? So, and if you find that this AB is also symmetric, that is equivalent to say that this AB is equals to EA. Okay, so what we really care about much of this symmetric matrix is about its eigenvalues and eigenvectors. Okay. All the symmetric matrix will have very nice properties for their eigenvalues and eigenvectors. So here, okay, suppose I have this n by n symmetric matrix, and then it always has n eigenvalues, right? So and of course, it's possible that some of them are repeated, but anyway, so there are n eigenvalues, and then corresponding to n eigenvectors. Okay. So what are the nice properties? Okay, the nice properties are that all the eigenvalues are real numbers. Okay. Okay, so although I didn't really talk much about the case when we have eigenvalues being not real, but I did give you an example before, right? So if you still remember the example that I have given is that remember the rotation matrix. Okay, remember the rotation matrix if you go back to the last part of the chapter. But anyway, so if remember, we call the rotation matrix. Okay, so and if you go ahead and find the eigen values, okay, so you might still remember that this one does not have real eigenvalue. You might still remember that I think I told you that the eigenvalue would be this. So that means here I'm not focusing on this matrix particularly. I'm just reminding you that yes, sometimes complex eigenvalues will occur. Okay, so although most of your homework problems or in other example in the lectures is focusing on the real eigenvalues, but still remember, sometimes complex eigenvalues does occur. Okay. But here what it tells us is that whenever you have a symmetric matrix, okay, then it is guaranteed that all the eigenvalues are real numbers. And so this is one thing nice. Okay, so and actually the proof is not very long and complicated. I'll actually talk about that. And the second nice property is that so suppose I have this all the n eigenvalues to be distinct. Okay, so then it is guaranteed that the eigenvalues corresponding to different the eigenvectors corresponding to different eigenvalues are orthogonal to each other. So that's two things very nice. Okay, and also moreover, okay, so even though sometimes if you have some repeated eigenvalues over here, which we talked about before, right? So suppose if one of the eigenvalues has this k-fold degeneracy, okay, so even that happens, so it is guaranteed that you can always find k linearly independent vector that corresponding to that degenerate eigenvalue. Okay. And again, if you go back to the last part of the chapter, you might still remember that it is not always the case for any matrix, right? So if I have given you an example that if I have repeated eigenvalues, okay, so and that repeated eigenvalues sometimes really just give you one vector. Okay. But here, if you are symmetric matrix, then it is guaranteed that you can find the k corresponding linearly independent eigenvectors. And remember, when we have that kind of situation, when I say that I have the suppose I go back to the simpler case, right? I have this twofold degeneracy, right? So you may still remember that. Then I will having any combination, any linear combination of the two linearly independent eigenvectors to be the eigenvectors. Right? So that is in an example that I gave maybe last two lectures. So I have, for example, if your eigenvectors is written like this, some constant so you find that, right? So any linear combination of these two linearly independent eigenvectors are the eigenvectors. Then you can always we express it as some something like this: k1 prime 1 0 plus k2 prime 0 1. So you can always choose again, right? So instead of having these two vectors which are linearly independent but not orthogonal, but here you can always make the choice to pick the two that are orthogonal to each other. Okay. So I'll give you an example later. Okay. So but here I'll come back for that. But first, if you just consider the overall picture here, is that 2 and 3 properties, the properties 2 and property 3, really are telling you that there are always n linearly independent eigenvectors. So not only that, n orthogonal eigenvectors, but linear independence is enough, right? So, but then that would mean that well, whenever you have the n linearly independent eigenvectors, then I have mentioned before, and that means that the matrix can be diagonalized. And that means symmetric matrix can always be diagonalized. Okay. So let me spend a bit time on quickly go through the first property, the proof. Okay, it's actually not very long, it's very short. So all eigenvalues are real numbers. So the strategy that we are going to we are going to approach it is that we are going to prove that whenever you have an eigenvalue lambda for the symmetric matrix, and then this lambda would be equals to its own complex conjugate. That's what we are going to try. Okay. So if that is satisfied, so that means lambda must be a real number, right? So this bar, right, so means the complex conjugate of a number. So I hope you still probably have learned this, right? So if z is this complex number a plus bi, then the z complex conjugate is given by a minus bi, right? So that's why if z is equal to z conjugate, then this z is a real number, right? Okay, so that's then let's see how to prove it. Okay, so suppose, right, so I have already found an eigenvalue and the corresponding eigenvector of a matrix A. Okay, so then I can write it like this. Okay. So now I'm going to take the complex conjugate of both sides of this known equation. Okay. But okay, so let me pause here. Is that so what does it mean by taking the complex conjugate for this matrix and vectors? Okay, so all it means is that when I say that I'm taking a complex conjugate of a vector, all I mean is basically is that I'm looking at each element in this vector or matrix, okay, and then turn that element to its own complex conjugate, right? So then that means, suppose I have this 2 by 2 matrix with this A, B, C, D, right? This is my A matrix. Then the complex conjugate of this A matrix is nothing but, right? So taking the complex conjugate for each element individually. Okay, so that's all it means, nothing more. Okay. So now, as I said, so if I'm going to take the complex conjugate of this left-hand side and the right-hand side, then I get this, right? So the product of A and V complex conjugate is equals to the lambda times V complex conjugate. And now, remember that we are considering a real matrix, right? So although we are kind of suspecting whether the complex, the eigenvalues is complex or not, right? So, but the matrix A itself, we know that it's a real matrix because that's what we are considering, right? And also, okay, so for the V, which is the eigenvectors, we are also suspecting whether it is real or not, right? So we don't know yet. Okay, so and you might ask, so why can eigenvector to be complex if I have a real matrix? But again, let me go back to this example here. If you go ahead and try to plug this eigenvalue back to this matrix here, you will find that the eigenvector is this 2. Okay. So the procedure is exactly the same. It's just that you allow complex number to appear in your linear equation, but you will indeed find that you can try by yourself. Is that for this matrix, so it's still a real matrix, but at the end you will have complex eigenvalue and complex eigenvectors. Okay, so that's why it is possible, right? So for real matrix to have complex eigenvectors, we don't know yet. So that's why, okay, here, as I said, if I take the complex conjugate for both sides of this equation, okay, so then here it looks like this. Okay, so the A conjugate, we know that it is A itself. Okay, however, the V conjugate is a V conjugate. We don't know whether it's equals to V or not. Okay, so we don't know yet. So then this A V bar is equals to this lambda bar V bar. Okay. Okay, so now what I'm going to do next is that I'm considering a dot product over here. So this dot product, what is this dot product here, right? So this is the dot product between the V conjugate vector and this vector AV, right? So, and this dot product, right? So if I just go ahead, right? So to replace this, right, product AV by this lambda V, then it's written like this. And that is, if I further take this lambda out, then it's lambda times the dot product between V conjugate and V itself. Okay. So this is the first result. Okay. So for this result over here, right? So you can write it anyway, even without relying on the symmetric property of the matrix A, right? So the first line you can write it for any matrix, right? So as long as you have this eigenvalue and eigenvector. Okay. So then the second line is the key. Okay. So this time I consider the same dot product. Okay. But here I'm going to rely on the symmetric properties of the matrix A itself. Okay. So you need to see you need to grab the key difference between this step and this step over here. So let me write it over here. Okay. So just take this step. Okay, just go down over here. Is that this one is written like this, and this A, right? So this A, using the fact that it is a symmetric matrix, then this step can be written as V bar T A T V. And then remember the basic property for transpose, right? So is that if you go back here, you use this property. BT AT equals AB together T. So that's why VT AT is equals to product of A and V bar together T V. So, and this is how we get to this step over here. So now this product A and V bar, V conjugate, is given by this lambda bar V bar, right? So as I have already constructed over here. So now this lambda conjugate V conjugate transpose, right? So, and basically is that the lambda can be taken outside of the conjugate, right? So because lambda itself just a scalar, right? So the transpose doesn't do anything. So then it will become to lambda conjugate times the dot product of this V bar and V. So then we start with the same expression over here, and then we obtain two slightly different results. First one is lambda times this dot product, and the second one is this lambda conjugate times the second dot product. So that means this has to be equals to this. And by definition, okay, so V itself is not a zero vector. Right? By definition, the eigenvector is not a zero vector. Otherwise, that's not a core eigenvector. Okay, so and that's why that means we have lambda equals lambda bar. Okay, lambda conjugate. So that's what exactly we want to show. Okay, so lambda equals lambda conjugate. So that means lambda itself is real. Okay. So the second property, which is the other very nice one. Okay, the third one is actually the one that we won't go there. Okay, but the second one I also give you the proof. Okay, so is that the eigenvalues corresponding to different, the eigenvectors corresponding to different eigenvalues, okay, assuming that they're all distinct, they're all different, are orthogonal to each other. So okay, so for this part, okay, I think I will just leave it for yourself. Okay, so again, not too difficult to follow, right? So the key is to make use of A equals A transpose. Okay, you will be able to show that if you have two different distinct eigenvalues, then the eigenvectors corresponding to the two distinct eigenvalues are different. So the second thing that the second example, the second type of matrix that I want to talk about is the so-called orthogonal matrix. Okay, so actually we are not done with symmetric matrix yet. Okay, we will actually try to diagonalize a symmetric matrix. Okay, but I need to introduce this so-called orthogonal matrix first, because it will appear when we try to diagonalize a symmetric matrix. So this is called an orthogonal matrix. Is the definition, it's not difficult, is that the transpose of this matrix Q, okay, will be equals to the inverse of itself. So for symmetric is that transpose equals to itself, but here is the transpose equals to its inverse. And in fact, okay, if I have this, the other way to say it is that I have this QT or QTQ equals to the identity matrix. Okay. And in fact, you can go back to what I talked about earlier in this lecture, right? So is that when we have this matrix P, okay, which is constructed by an orthonormal basis. So remember earlier, I just told you that if this matrix P, right, so it's constructed like this, then actually PTP is an identity matrix, right? So, and that means, right, so if you have this matrix Q, which is constructed, okay, so by a set of orthonormal vectors, so then that matrix is known as an orthogonal matrix. Okay. So here are the two examples. Okay, so this is actually familiar to you, right? So this is actually a rotation matrix, right? So you can try that taking the transpose and then multiply with itself, right? So you find that this is indeed equals to the identity matrix. Right? And you can see that if you just look at column by column, right? So if you look at this column and this column, right? So you will, of course, realize that these two are orthonormal vectors, right? Because if I draw it on the xy plane, right? So this vector here is this one, right? And then this vector over here is this one. So see how it is constructed by two orthonormal vectors. So this is orthogonal matrix. So then the other example is 4 by 4, right? So this is actually also quite obvious, right? So you can clearly see that, right? So this one, this one, this one, this one, right? So it's you can see it just immediately that they form an orthonormal basis in a 4-dimensional space, right? So now this matrix Q, okay, so whatever how we construct it. Okay, so if we treat this matrix, right, so as a transformation matrix, right, so that is we take this Q matrix and then operate on taking the product with the column vector and then basically transform that column vector. And what will happen? So you realize that if you are going to take this Q matrix, right, so and then do the product with this vector, right? So and then what you have after transformation is some vector v prime. Right? So what is so special about this transformation is that before and after transformation, so the matrix, the vector preserves the length. The length of the vector is preserved. So that is the length of the original vector is the same length of the transformed vector. Why is it not difficult to prove? It's over here that if you take the dot product of this transformed vector with itself, right, so this v prime t v prime, which is by definition equals to this qv transpose qv, and then this qv together transpose is given by this v transpose qt, right? So then you have this v transpose q and v. And remember, okay, by definition, this is identity matrix, right? So this is the definition of orthogonal matrix. And then this two disappear, then you just end up with this dot product of the v vector with itself. So you can see that transform vector have this dot product. Okay, original vector has this dot product, and their values are equal. So this is a transformation that does not change the length of your vector. So then geometrically, so then the one common example, of course, is rotation. The rotation will change the direction of your vector, but it never changes the length of vector. So rotational matrix is an orthogonal matrix. And maybe another example is you can think of reflection. Okay. Reflection also, right? So you will take the mirror image of one vector, right? So it will change the direction, but then again it won't change the length of the vector itself. Okay, so next let's take a break here. Okay, so let's take a 10 minutes break. We'll come back at 12:35. So after the break, I'll actually try to talk about the diagonalization of this symmetric matrix. So now that we know, right, so a symmetric matrix must be able to be diagonalized. So then after the break, let's actually try to diagonalize symmetric matrix. Okay, so let's continue. So now we are ready to do diagonalization of symmetric matrices. Okay, and in fact, for diagonalization for symmetric matrices, okay, so we have a diagonalization that is known as the orthogonal diagonalization. Okay, I'll tell you how it is different from the diagonalization that we have talked about previously. Okay. And the definition of this orthogonal diagonalization is that if you have okay, let me quickly go back to the usual, the normal, the diagonalization that we talked about last time is the following, right? So if I have a matrix A, not symmetric matrix, any matrix, right? So if I can find a matrix P such that this product P inverse AP equals a diagonal matrix D, right? So then we have done the diagonalization. So this one is for in general, right? So any matrix that can be diagonalized, that can be written like this. Now, orthogonal diagonalizations, okay, simply means that the following, okay, so is that instead of having this P inverse, okay, we have this P transpose, okay, and in fact, this P transpose, okay, is the same as P inverse. So that is, if you find that a matrix can be diagonalized using this process, that is, you are able to find this P and P inverse to make this happen, and you realize that this P inverse is actually equals this P transpose, okay, so then this is known as the orthogonal diagonalization. Okay. We have this orthogonal name here because as I just told you that if this P inverse equals this P transpose, then this P is a orthogonal matrix, right? So that means A can be diagonalized using an orthogonal matrix P, right? So now we go back to the symmetric matrix, right? So it turns out that as I told you already, so symmetric matrix, you must be able to diagonalize it, right? So this blue equations always exist, right? And moreover, okay, you can always find this P inverse if you select it carefully. Okay, you can select a P such that this P inverse equals to P transpose. So remember when we try to diagonalize a matrix, right? So this, how do we construct this P? So you may still remember that for diagonalization, right? So this P is, how do you construct this P? You go back to the last part of the lecture, you may still remember that this P is constructed by the eigenvectors, right? Constructed by the eigenvectors. So that is, if you find, right, so for example, if a 2x2 matrix, right, so you find the two eigenvectors is V1 and V2, right? So then this P is formed like this, right? So, and remember that the V1 and V2, okay, sometimes, okay, you have freedom to choose, right? So especially in the case of degenerate eigenvalues that we'll talk about, right? So for degenerate eigenvalues, right? So if you pick this V1 and V2, right? So to be orthonormal sets, right? So then you will be able to satisfy this P inverse equals PT, right? But then again, right? So this is, sometimes it depends on how you choose it, right? So then this P inverse may not be equals to this PT. Okay. So let's do two examples. I hope it will be clear. Okay, let's do two examples. So the first example, okay, so this this is a symmetric matrix. Okay, you can see that this is a symmetric matrix. So I have done the calculation already in this one. But the next one, I'll leave it to you to do it by yourself. So, but anyway, just believe me that for this matrix, okay, so the three eigenvalues are 0, 1, and 6. So three distinct eigenvalues. Okay. And if you just follow the same procedure that you have learned to diagonalize the matrix, you will find that the corresponding eigenvectors are these three. And you can immediately see that these three form an orthogonal basis. So you can try to do the dot product, right? So if you take the dot product of this and this, what is this? It's 2 minus 2, 0. Right. So if you take the dot product of this one and the other one, so this one and this one, right? So it's the minus 2 plus 2, right? So now what after the normalization of the vector, okay, so these are orthogonal bases, but if you do the reward orthonormal, right? So if you normalize them, then you have these three vectors also. And then now if you go ahead and construct the matrix P, okay, so then you will find that this PTAP is given by this matrix here, okay, which is a diagonal matrix. So here, let's actually let me let you to do an example. Okay, so this is matrix like this. Okay, minus 2, 1, 1, 1, minus 2, 1, 1, 1, minus 2. So let me skip one step for you. Okay, so is that first of all, I'll tell you that this lambda is equal to 0 or 3, and the 3 is a repeated root. So, and now I'll just spend a couple minutes to try to find, okay, so for lambda equals 0, okay, so what is the eigenvectors? Okay, and then for lambda equals minus 3, what is the eigenvector? Okay, just spend a couple minutes on that. Okay, so in particular, so this example is important because again here we see the repeated root, right? So need to have some special care for this case. So just take a couple minutes to try the eigenvectors for this matrix. Oh, 寫錯. Okay. Let me check my answer again. Should be 應該係負3。你係計到 eigen？ it should be minus. Okay, so it's a typo. It's minus. Okay, and there's a typo in the last line. So this one should be 1. Okay. Okay, so let's try the lambda equals 0 first. Right, so the coefficient matrix that we have, right, there is minus 2, the lambda is 0, so minus 0, 1, 1, 1, minus 2, minus 0, 1, 1, 1, minus 2, minus 0. Right, so this is the coefficient of matrix of your system, right? So then Gaussian elimination, right? So what I'm going to do is that I keep the first row, right? So minus 2, 1, 1, and then I multiply the second row and the third row by a factor of 2. Then I have this 2 minus 4, 2, and then 2, 2, minus 4. Okay, so then I'm going to eliminate the second and the third leading coefficient here. Then I have this minus 2, 1, 1, and then 0, 0. And you find that this is minus 3, 3, 3, minus 3. So, and what it gives you, right, so is that, so of course the second and the third row are giving you the same information. Right, so like this. So then at the end, the equations that you get is the following, right? So minus 2x plus y plus z equals 0. Right, both the second and third one tell you that y equals to z. Right. So now y equals to z, and let's say these two equal to some three parameters c. Right. And then that means x, which is equals to y plus z divided by 2, that is equals to z. So that means x, y, z all are equals to a three parameter c. So that means the eigenvectors, let me call this v1, is given by c times 1, 1, 1. Right. Of course, the c is irrelevant here. So the first eigenvectors I find is 1, 1, 1. Okay. So this is not the tricky part in this problem here, right? So because I really want to talk about the repeated eigenvalues, right? So and here, this time the coefficient matrix, right? So minus 2, minus 3, right? So plus 3. So 1, 1, 1, minus 2 plus 3, 1, 1, 1, minus 2 plus 3. Okay, so then here, right? So again, Gaussian elimination is that you realize that they all 1, 1, 1. Okay. So, and that means the three equations give you the same information. Is that x plus y plus z equals 0. And then there are no any constraint for any of the two of the variables. So then y, I can take, as I said, a three parameter c1, and then z, another three parameter c2. So this time, right? So my eigenvector here is, what is it? What is x? X is minus y minus z, right? So this is minus c1 minus c2. So y is c1, and then z is c2. Okay. So here, right? So you can see that I can write it as a linear combination of 2 vectors. So I can write it in this form. Okay. So Are we done yet? Right, so here we have, in principle, we have already the 3 eigenvalues found, and then we have now 3 eigenvectors. Right, so let me also write it in front. So then in principle, right, what you can do is you're already able to diagonalize it, right? But still, that's the thing, is that it's still not an orthogonal diagonalization. So the reason is because with these 3 eigenvectors, I can, of course, construct this P matrix, right? So using these 3 eigenvectors, so 1, 1, 1, minus 1, 1, 0, minus 1, 0, 1, right? And such that if I construct the P like this, then the P inverse A P would be the diagonal matrix that is given by 0, minus 3, minus 3. So there's no any problem with this one, right? So we diagonalize it. However, this is not the orthogonal diagonalization yet. Okay, it is because in this case, you can try by yourself, but you realize that this P inverse is not P transpose. Okay, it's not. Try by yourself. And the reason is because the 3 eigenvectors that we pick, right, not normalized and also not orthogonal yet. So because if you look at these two, don't care about the first one. So just look at these two. Take the dot product between this one and this one, not 0. So this one and this one are not yet orthogonal set. Right, so you take the dot product, what do you get? Minus 1 times minus 1. So 1. Okay, but you, of course, you know that this is linearly independent set, right? So, and if we want to orthogonally diagonalize it, we need to select another set of eigenvectors for these two, okay, such that these two are orthonormal. So, okay, so geometrically, what happens? So these two vectors will form a plane, right? So I just need to rely on that plane and then select a set of select two orthogonal vector. Okay, so let me just write down. So let me just draw the picture. Okay, so the two eigen vectors that we have from the last slide is that one of them is like this. This one is my minus 1, 1, 0. Okay. And then how does the other one look? The other one is somewhere over here. That is minus 1, 0, 1. Okay. This one lie on the XY plane. The other one lie on the XZ plane. But they have some angle, but this angle is actually not 90 degrees. Okay, so we have to, right? So these two will form like the plane, something like this, right? So you need to go to this plane and then select two orthogonal eigenvectors. Okay. Then here, let me I want to just do it once. Over here is that how do we, given two linearly independent vectors, but not being orthogonal, how do I take another set such that the new set are orthogonal? So here, let me. So here, what I really want to do over here is that so instead of having, so let me call this, let me label them. So I'll just, let me just call this V1. And then this is V2. Okay. And then just forget about the actual values. Okay. Just two vectors anyway. Okay. So I don't want this V2. Okay, I want another vector, this V2 prime, such that this V1 and this V2 prime are orthogonal. But and all these three vectors lie on the same plane. So then that is, I just want to try to find V2 prime, okay, out of the original two vectors. Okay, so if I just try to look into this inclined plane and draw these three vectors one more time, okay, so I will have V1, and then this is my V2, and then I want this new V2 prime. So V1 is known, V2 is known. I want to get V2 prime, such that V1 and V2 prime form an orthogonal set. Okay. So first of all, right, so this V2, I know that it can be written as a sum of two components, right? So is that, also let me define one more thing first. I define this V1 hat to be the unit vector along V1. Okay, so similarly, I define this and also let me also define the unit vector for the V2 prime. So I define all these three unit vectors. Let's go along these three vectors. So this V2 can be expressed as some component, some coefficient times V1 hat plus some other component times V2 prime. So what C1 and C2 really means is C1 means the projection of this vector onto V1. Right, so this is C1. Okay. And then this C2 is the projection onto this V2 prime, which we don't know yet. Okay. I can write it this way. So at the end of the day, I want to know this V2. So now, what is C1? C1 is, as I said, is the projection of V2 onto this V1 direction, right? So that means this C1 really is the dot product between this V2 and V1 hat, right? And then similarly, this C2 is the dot product between this V2 and V2 prime hat, right? If this is clear. So now I put this V2 prime as the subject. So then that means C2 V2 prime is given by V2 minus C1 V1 hat, which is V2 minus, what is C1? C1, as I said, is this V2 dot V1 hat. So it's this V2 dot V1 hat, V1 hat. So now we know we certainly know how to find this V2 prime, right? Because we know this V2 and V1 already. So let me write one more step over here. Okay, is that this is really this one minus this V1 hat is given by V1 divided by V1 magnitude. So then I can write it this way. So then it is just taking some dot product over here, right? So that's actually to be straightforward. So this is the key, right? So this one equals this one. So now if we go back to our problems, okay, and then putting the two vectors, this V1 is, as I mentioned, is -1, 1, 0, and then this V2 is -1, 0, 1. Okay, putting these two into this formula, okay, then you will be able to find that this C2 V2 prime is given by, what is V2? As I said, V2 is -1, 0, 1 minus this dot product. So at the end, you get these two factors. This. So that is now, instead of taking originally, right? So instead of originally, we have these two to be the to be selected to be the eigenvector. So now, right? So we don't want these two, right? So we want, well, this one still, but then also two. So then we have this orthogonal set. Right? So that is, let me write down the summarize the result in the next slide. So for lambda equals what? The 0, right? The lambda equals 0. The eigenvector, it must be this one. There is no choice for that. Right. So and then for lambda equals -3. Okay, so now we take these two. Okay. now if you go ahead and try to see if they are all orthogonal to each other, right? So you can go ahead and try that, right? So this one dot, this one is -1 + 1, 0. And then this one dot, this one 1/2 - 1/2, 0. This one dot, this one also 0. Okay, so now we are all good. We are able to select this orthogonal set of 3 vectors. Just one last step, orthonormal. Right? So they are orthogonal, but each of them, right? So I want them to have the unit 1 to have the length 1, right? So then this one need to this factor over here, right? So this one I need this factor over here, and then this one I will need this factor over here. So with this, if you construct this P matrix, using these 3 orthonormal eigenvectors, then you will have this. Okay. This matrix can also help you diagonalize, right? So this matrix can help you diagonalize. This matrix also help you diagonalize. But this is the orthogonal diagonalization, because this time you'll find that P inverse equals PT. And then that is, right, so P inverse AP equals to diagonal matrix D. And you can now simply write this PT AP equals diagonalized matrix D. So here you can see that the orthogonal diagonalization, the procedure is the same, except that when you construct your P matrix, right, so you have to make sure that all the eigenvectors at the length 1, right, and also whenever you have this degenerate eigenvalue, make sure that the eigenvectors that you pick are orthogonal. Again, if you don't have the degenerate eigenvalues, life would be much easier, because in that case, you don't have any choice in picking the linear combination for the eigenvector. So in that case, you just need to make sure that you remember to normalize each of the eigenvectors. Yeah, I don't have much time left, but give me 5 more minutes to quickly talk about this one. Is the so-called conic section. So I believe that you have learned about conic section before, right? So the circle, ellipse, hyperbola, parabola, right? So there's 4 so-called 4 different shapes of a conic section, right? So and here, right? So for example, if I have an ellipse like this, you know that it can be written by this equation. So and you understand that instead of having this, right? So if you have a minus sign instead of plus sign, you know that it's a hyperbola. So, but let me just focus on ellipse, okay, to make the point. Okay. So one thing is that before going back to this picture, okay, so I want you to consider one thing. Is that I have a matrix, this symmetric matrix, and then multiply with this vector, and then take the, so it's the dot product of this xy vector with this whole thing, right? So, and if you go ahead and try to do it, right? So the way you do it is that you can just keep the first one by itself and then do the second and third first, right? So you find this AC plus dy and cx plus dy, and then do the second step, and then at the end you will find that this is equal to ax squared plus 2cxy plus by squared. Okay, so no problem with that, right? So we have an x squared term, y squared term, and a cross term. The cross term is the multiplying x and y. Okay. So then, of course, if you have a case where this matrix in the middle is just a diagonal matrix, right? So then, of course, you have something simpler, right? So in fact, the cross term will go away, right? Just like this. Okay, so now I want you to go back to this ellipse and think about this equation over here, okay? And try to write the left-hand side into this form, okay, which I call the matrix form. So you realize that the left-hand side of this equation can be written like this. Right. So, and that is equals to 1. So this ellipse equation, or you can imagine other conic shape equation, can be written as this matrix form like this. Okay. So now consider a case where I rotate the ellipse. Okay, so I rotate this ellipse to like this. Okay, bad drawing, but you understand the idea, right? So I rotate it like this. So now, maybe you have learned it before or not, but if you have a rotated ellipse, you understand that the equation doesn't look like this anymore, right? But instead, you do have some x squared term, y squared term, and some xy term. That cross term comes up. So now, if we consider another coordinate system that looks like this, that still follow along the two axes of the ellipse. Right. So I have this new coordinate system. Okay. So in this new coordinate system, then the ellipse itself is not tilted. In this new coordinate system, right? So then the ellipse will still be written exactly like this form, right? But this time, of course, I need to use x prime and y prime instead of xy. Right. So in the new coordinate system, this form here. So now, I have rotated a coordinate system, right? So how do I get x, y to x prime, y prime? It's a rotation. It's rotation, yes. So, and right, so someone pointed out, right? So is that if you go back to the last part of this chapter, is that we are rotating the coordinate system and given by this coordinate of this rotation matrix. Remember, we are rotating the coordinate system, so in the anti-clockwise. So then actually that is given by this So make sure you know why I have the minus sign over here, but not here. Okay. So now, if you go ahead and put this relation back to this equation, okay, just to save me some time, I just call this Rxy. So then the second equation here can be written like this. So 1a squared 0, 0, 1b squared Rxy times x prime, y prime, which is xy times RT. Right. So now, if you look at this whole part here, so this is a product of these three matrices, and you can, if you try, right? So to multiply this rotation matrix, right? So to this and then multiply by the other rotation matrix, you will realize that this is a non-diagonal matrix. Okay, a non-diagonal matrix, and then that's why this whole thing will have something x squared plus something y squared plus something times xy. So that is why in this tilted ellipse, right? So if you use this original coordinate system to look at it, right? So you will obtain this more complicated equations, right? So with this cross term, right? So instead of this one. So that is okay. So I'll go through this example next time. So that means, right? So in other words, right? So if I give you this equation to start with, right? So with some cross term already, and just looking at this, right? So you don't really know how the ellipse looks, right? So but if you understand that this cross term, right, can be removed, actually can be removed by picking a suitable rotation of the coordinate system, right? So that in that coordinate system, this cross term will not be here, and then that you will see nice and clear is an ellipse equation. Okay, so but okay, I overrun a lot, but I will stop here now.